I just sum over all the possible k in one dimension. Now I just replace that expression in terms of this. This is my Hamiltonian. So I have this h of k, but then this h of k is going to look just like that. So I will write 1, and the rest will be just like there, so I don't have to rewrite them. And so on and so forth. So it's very similar. That's why I started with Kitaev's model. And this is going to look very similar. And I can again also write my my Bogoliav of quasi-particle operators. Again, they will be expressed in UK, CK, and so on and so forth. So it's exactly the same, except one is a two-dimensional situation and the other is one-dimensional. Okay? So I'm going to save time, not going through that. And again, I can also ask whether I have a topologically trivial or non-trivial superconductor. And so again, you can consider, just like before, consider this vector called h of k. So I'm going to keep all those, and I'm going to deal with a two-dimensional situation. I think a lot of the things I have to do in a moment will be, I can only keep them more or less qualitatively. I don't have time if I want to give you all the key concepts. So again, we consider h of k. You write it as the small h of k dot Pauli spin matrices. So the same trick we have done earlier, okay? And it turns out, and you can start examining this situation. So I can define this h hat is this h of k divided by its absolute value. And then we just see how this h hat, how it points around. So for mu smaller than 0, what you will find is that, so I will save time, just give you the answer. When k is approaching 0, this vector is going to point along North Pole. And when h of k, now k can go to infinity. If k goes to infinity, this is back to the North Pole. So what is this telling me? Or telling you? This is trivial, right? When I consider this vector, it goes around and eventually goes back to itself, I'm doing nothing. So 虚功, right? So it's topologically trivial. However, if I have mu greater than 0, then h hat, k equals to 0, is pointing along the South Pole. And then h hat, k goes to infinity, pointing to the North Pole. So now I sweep around the sphere, half a sphere, and this gives me effectively a Chern number. This is a way of looking at things. Chern number is -1. And what's my Chern number? I can define my Chern number. I mentioned that a little bit yesterday. So I just look at these vectors, H vector, and of course, what's my hx? These things actually have meanings. This is a real part of the energy gap. And hy is the imaginary part of the superconducting gap. And hc is the normal component, the normal state energy. So it's a similar trick. I'm still examining the situation to see whether I have a topological so what I can do is I can plot things like the following. Do I want to plot this? Let's see. If I have time. Well, anyway, you already, let me skip that, because I have a lot to mention. So anyway, so you can examine the situation that you actually depends on your chemical potential, whether it's above or below zero. You have a topologically trivial or non-trivial state, and in this case, you have turn number equals to -1. Now, what you can do is that if you have Px minus IPy, superconductor, turn number will be +1. Okay? And now if you have an F-wave superconductor, your turn number can be -3. But these will be some non-trivial numbers. So you can play around and start constructing, replace your superconducting pairing part. This part is P-wave. So you can play around. So here if you have derivative x minus I derivative 1, you will find a turn number is 1 and so on and so forth. You can do it as an exercise for yourself. But anyway, it's a topologically non-trivial situation. F-wave, which what I know in F-wave basically you can write kx plus iqy to the power q. That will be F-wave. So it's the momentum number 3. Okay, that's all fine. Now, so I want to move on to the next. So we have a topologically non-trivial situation. That can exist. So we know that. Good. And then, so what should we do? We're going to construct something. I won't run on those. Remember what I'm doing right now is that I first tell you we have a topological insulator. And then between the interface of a topological superconductor, topological superconductors and topological insulators are in many ways very similar. Both have gaps. In one case you have a phase coherence, the other you do not. But in any case, so I have a topologically non-trivial state. So that's fine. So I'm going to erase all these. Because I want to do more run-on modes. So I want to somehow have interfaces between the topological superconductor and the trivial vacuum, right? So that's what I want to do. So how do I do that? Well, I can do the following. I can construct an annulus. So this is what I was hoping to be able to derive from you, but I think I'm quickly running out of time. So I will just describe it qualitatively. But in principle, you can solve this problem. So I have an annulus like this. And so inside, so this shaded area is a topological superconductor. And inside, I have mu greater than 0. So it's topological. Outside of which, I have topologically trivial states. Okay? So in this case, and I have a radius. This external radius, I call it R out. And this internal radius, I call it R in. Then what's happening is the following. It turns out that when you have such a situation, so you have interface between a topological superconductor and vacuum. Then what I'm going to have is that I will have Majorana modes. This can be rigorously derived, but I'm out of time. I will have Majorana modes going around. Inside will be the in and out will have the opposite. When you solve the Hamiltonian for this situation, so I will write my Hamiltonian now for the edge states. So this is the total Hamiltonian for the bulk. If I write it for the edge, then of course, this I will use cylindrical coordinates for convenience. And because I'm out of time, I'm not going to solve this directly. But if you just believe what I said, which you can independently verify. Generally, I don't like to tell people to believe what I said. You should verify it on your own. But we are out of time. So what I want to tell you is you take this Hamiltonian, and this theta, so I have this theta. This is theta angle, right? And r is this radius. So r is the radius, and theta is this angle. I write this thing in polar coordinates. And then I can do a gauge transformation. I can gauge away this theta and do various things. It turns out you will find that the solution for your edge states will be two oppositely propagating Majorana modes. So that's one thing. And also, these actually will have, because naturally you can imagine that, so you can prove that this wave function is a Majorana function because Majorana fermion, because its creation and annihilation operators are the same. I don't have time to show you this because this derivation alone probably will take half an hour. And we don't even have half an hour, we have 20 minutes left. But this is the situation that you will have. So I will just do qualitative description. You also have an energy spectrum that looks like the following. For this picture, you have an energy spectrum looking like this. It turns out, well, you have a finite radius, and you have this circulating function. Actually, you can have it in integer numbers. And so what happens is that you will have n is integer. And you will see discretized energy states. These discretized energy states will look like this. This is one half. I'm not drawing this very well. This is one half. This is a half integer. And then I should double this. So these are the energy spectrum. And this is with E, the energy spectrum for the internal part, and this is for E out. You will actually have this discretized energy spectrum. So if I write my wave function, I can actually write my wave function. So E out is. So I'm sorry, this part I'm not proving it. I don't have time to prove it. But this is the solution. Your energy spectrum for the outside will actually be related to an integer times the superconducting gap over the radius. And your E in are, sorry, this is R out. So I should just have, yeah, R out. Because I'm only considering the edge state. This will be minus N delta R E. Okay. So these are my energy spectrum, and I can write my wave function in terms of these discrete states. And you only have to worry about the positive energies because there's a relationship of creation and annihilation. Because as you see, if I reverse n and minus n, I can have similar solutions. And so you don't have to worry about the negative energy part. And so if you write your wave function, separate Marana modes at any special point until I do something. So these are finite energy. So this is zero energy. So I have a problem. These states, what's happening is that these states all require a finite energy. There is no zero energy state. And the wave function, so if I look at the wave function itself, it's related to some other solutions. This is some other wave function. And you can break it into both inner and outer part. Sorry, I'm out of time, so I'm not writing this out. You can look up the references. But this gives you an idea that my total wave function consists of inner part and outer part superposition. And then you will also find that these special quantities here, in or out, this thing has a special situation. You make n2 minus n, this will be the same. And so if I write gamma in, out, for summing all of the n values, this is the punchline here. You see this is exactly equal to think of this as a wave function, and then this, you sum over all of the possible n's, but because n and minus n has this special relationship. So in the end, this is really a Marana mode. The creation and annihilation operators actually are the same. Okay, but I have a minimum excitation energy. These are the chiral. They are chiral Marana nodes, but they have finite excitation energy. Minimum excitation energy, because n is an integer, so the minimum energy separation is 1/2 of that. So it's 1/2 of R in, out, superconducting gap. There's a minimum energy requirement. So you say, okay, yeah, so what should I do? There's something very interesting. This is when you don't apply a magnetic field. Now, if I apply a magnetic field out of this annulus, so what I'm going to do next is that I will insert a flux quantum into the annulus. And it turns out, again, I don't have time to derive it, but if I have one flux quantum coming through this, it turns out you can use magnetic flux to play around situation. And then when you insert one flux quantum, actually when you go around this, in this case you have anti-periodic situation when you go around. You pick up a negative phase, because your angular momentum is 1, so you pick up a negative phase. But now if I have an extra flux in there, it turns out it becomes a periodic situation. So it's no longer an anti-periodic situation. And so my energy spectrum is going to be different. So I'm going to use, if I insert flux quantum, my energy is going to look like this. So that means I have a Marana, zero energy Marana mode when I insert a flux, so which is great. And so that turns out to be one way. When you have an annulus looks like this, you have one flux quantum. You can consider it as if you have a branch cut. So I can imagine the following scenario. If I have a flux threading through this this annulus topological superconductor, so I would imagine we have other colors. Okay, there's a yellow. So it's almost as if I can think of it that way, that I have a branch cut. So you think about when you have a branch cut. So I go around, I have my Morana mount going around, and it's supposedly it's a P wave. So when I go around, I should have an anti-periodic condition. But now if I hit a branch cut, I have to change sign again. So if I go around, initially I have to change, I have a minus sign, I pick up minus sign. Now I have a branch cut. Whenever I go across a branch cut, I can think of it as if I have to pick up another negative sign. And this is conceptually very convenient. Then whenever you count the number of branch cuts, then you will know whether you have, you can isolate any, when you have a branch cut, you can actually have an isolated magnetic Marana mode. And so you go around, you actually can pick up an extra minus sign. And so here, then you have a plus sign here for this situation. This can be solved exactly. Okay, so that's one way of thinking about things. So if I have a topological superconductor looking like this, and I have two holes now. So I have two holes, and so initially I have my currents going like this. So the outside current, and now you might have two flux quantum threading through this. So I can draw like two branch cuts. So then if I look at, I have one flux quantum and another flux quantum, and I have this annulus, so I go around. And then we're seeing this scenario is that I go around this thing, I will have periodic boundary conditions. Again, because I have anti-periodic, but then I have a branch cut, so I become periodic. But for this guy, going around like this, it will be anti-periodic, then periodic, and anti-periodic. So the external current will be anti-periodic, and the internal current will be periodic. So this is one way of looking at if you have branch cuts, and you can actually have additional sign change. So with these stories, all right. So this is the second case. And so what happened is that for those of you who know something about superconductors, this looks interesting, right? You know when you apply a magnetic field into a type 2 superconductor, you generate vortices. And when you generate vortices inside the vortex, it's almost like normal. It's a normal material. So if you have a topological superconductor, you apply magnetic field. Then inside the vortex, you can consider that part as a normal core. So it's topologically trivial. So it's similar to this kind of situation. So you can imagine that if you apply a magnetic field to a topological superconductor, you can have a similar situation like this. Except now you have one flux quantum. So it will be a situation like what we have described there. So I have told you two cases. It turns out that, okay, I think I have a case 3. Let's see if I have a two-dimensional system that has all of the spins. It has a spin triplet superconductor. In that case, it's yet another special case. Never mind. I think I'll skip that because that's a. Okay, what that is that you have a full spin configuration. You have a triplet superconductor. Do you know what a triplet superconductor is? Singular superconductors means you form Cooper pairs. You have spin up and spin down. That forms a Cooper pair. A triplet superconductor means that you actually have parallel spins from the spin triplet situation. When you have a triplet situation, you can either have spin up or spin down. You cannot ignore the spins. Actually, you have a vector that's describing the spin orientation. But it turns out in a two-dimensional triplet superconductors, if it's also P plus IP, if you apply a magnetic field, magnetic flux, and it would look kind of trivial. But what's happening is that when you apply half a flux quantum and you go around the vortex, actually you can isolate the spin up and spin down configuration. And one of the spin species would see it as a trivial situation. the other spin species will pick up this, this extra half of flux quantum, will only couple to one of the spin species. So you effectively separate out your Kramers partners into only one spinless situation. So you spin polarize it. So that's the idea of this third situation I was going to mention. And then if you, the fourth situation again, I can pretty much skip. You have time reversal invariant two-dimensional superconductors. If it has full spin configuration, you can actually effectively split things into P plus IP and P plus minus IP. So you have counter-propagating chiral for Majorana modes, just similar to this situation. So you can also have Majorana modes in that time reversal invariant two-dimensional superconductors. So I'm just waiting, just quickly going through. But the last thing I do want to tell you, so I will go a little over time, but this is an important concept that people try to construct realistic situation. So all of these things I have described so far, you may say, okay, they're not typical superconductors. We cannot easily find spinless superconductors. We cannot easily find P-wave. But actually, there are ways you can do without having to really have a P-wave superconductor. You can effectively induce the P-wave superconductor. In the interest of time, I will just do qualitative description. So how do you do that? I have erased the board, but I did mention to you before, to realize Majorana modes, you need three ingredients. The first ingredient, you need superconductivity. The second ingredient, you want to break time reversal symmetry. Because time reversal symmetry gives you Kramers pairs. You have spin up and spin down. You cannot eliminate spin up and spin down. So you want to break time reversal symmetry, you separate out your two spin species. So that's the second ingredient. The third ingredient, you want to have strong spin orbit coupling. And that gives you special energy states. So when you have those three ingredients, you can sit down and start thinking about all kinds of different possibilities to construct an effective Kitalyov's model. So one way we can do is that we can do the following. If I have a one-dimensional electron gas, and it can be due to anything, 1D electron system. But I will have in proximity with superconductivity. And most superconductors, you have a lot of superconductors that are S-wave superconductors. You can have a one-dimensional system in proximity with an S-wave superconductor. And then you can apply a Zeeman field. So I can say under a Zeeman field. So a Zeeman field can be induced either by a magnetic field or by ferromagnetism. So that's related to spintronic construction you can do. So I have a Zeeman field. So these are the ingredients. Then you can prove that you can satisfy all these interesting situations. So what happens is that your total Hamiltonian will be related to your one-dimensional electron system plus your superconductor in proximity, and then the tunneling between the two.